Welcome to the video on polar form and Euler form. First, we'll talk about these two forms and what they look like. So for both of these equations, r is the modulus, which is the distance from the origin. So it's the square root of a squared plus b squared, and your a and b are from your Cartesian form, where you have a plus bi. So it's the square root of your real part squared plus your imaginary part squared. And then theta is your argument, which is the clockwise angle from the positive x-axis. So theta equals the inverse tangent of your imaginary part over your real part. So in polar form, z equals your modulus times your cosine of your argument plus I times the sine of your argument, which cosine theta plus I sine theta can be rewritten as cis theta. So your polar form is r cis theta. And then your Euler form is r times e to the I times theta. So it's your modulus times e to the I times your argument. So when we're adding, multiplying, or dividing complex numbers, there's different things you need to do to combine them depending on which form you're in. So if you're in polar form or Euler form, to find the sum of two numbers, you need to convert them to Cartesian and then add them, because you can't add them any other way. For the product, you're going to multiply your modulus, so your r values, and add your arguments, so your thetas. And you'll do that with both Euler and polar forms. And then for a quotient, you're going to divide your r values and subtract your theta for both of them. We'll do some practice problems with those later, but for now, here are the formulas. When you're in Cartesian form, you'll add your real values, your a values, and then you'll add your imaginary values. So it's just combining like terms. So these ones, and then your imaginary values. When you're multiplying in Cartesian form, you use the distributive property. So you'll multiply your first values, your outer values, then your inner values, and your last values. So that simplifies to this, because your last value would be b1 times b2 times I squared, and that I squared became this negative here. And then when you're dividing in Cartesian form, you're going to multiply the numerator and denominator by the conjugate and then simplify. So for example, if I had 4 plus 3i over 2 minus 6i, to divide them, we'd multiply it by 2 plus 6i with 2 plus 6i on the numerator. That way you can get rid of the imaginary component in your denominator. So this would equal 4 plus 36 in the denominator, and your numerator would be 8 plus 30i minus 18. So this simplifies to negative 10 plus 30i over 40, which can be separated to negative 10 over 40 plus 30 over 40i. So that way you can split it into your real component and your imaginary component. So that's negative 1/4 plus 3/4 I. So here we have our first three practice problems. It says add, multiply, and divide the expressions. So we'll start by adding. We have 6 plus 3i plus 3 plus I. So this is in Cartesian form. So we'll add by adding the real part and then the imaginary part. So our real part, we have 6 plus 3, so we get 9. And then our imaginary part, we have 3i plus I, so we have plus 4i. Next, we'll multiply them. 6 plus 3i times 3 plus I. So we'll multiply our first terms, which gives us 18. Our outer terms, plus 6i. Our inner terms, plus 9i. And then our last terms, plus 3i squared. So I squared is going to be negative 1, so this will become a minus 3. So we have this equals 18 minus 3, which is 15, plus 6i plus 9i is going to give us 15i. So there's our answer when we multiply it. And then finally, we need to divide the expressions. So we have 6 plus 3i over 3 plus I, which will multiply by the conjugate. So the conjugate of the denominator is 3 minus I. So we'll multiply by 3 minus I over 3 minus I. Our numerator, when we multiply, we'll get 18 minus 6i plus 9i minus 3i squared. And our denominator will be 9 minus 3i plus 3i minus I squared. So the minus 3i and plus 3i will cancel. The minus I squared is a minus -1, so it'll be a plus 1. And then on our numerator, this minus 3i squared is going to turn into a plus 3. So that simplifies to 18 minus 6i plus 9i plus 3 over 9 plus 1, which equals 21 plus 3i over 10. So we can separate this into an imaginary and real component by just taking our 21 over 10 plus 3 over 10i. So here's our added, multiplied, and divided solutions. So for the second problem here, we have polar form. So we're going to add 27 cis 30 plus 3 cis 50. And it's important to remember that our angles here are given in radians. So we can start by drawing a triangle because we need to convert this to Cartesian form. So our radius is 27 and our angle is 30 radians. So we're trying to find A and B. So our A values are going to be our radius times the cosine of theta, and our B values are going to be our radius times the sine of theta. So when we're adding it, we'll have our 27, our radius, times the cosine of 30 radians, and our other A value will be our radius, 3, times the cosine of 50 radians. So this will be our new A value, and then our B value will have plus I times our radius, 27 sine 30, plus 3 sine 30. So when we enter those values into the calculator, we'll get our Cartesian form of the sum, which is 7.06 minus 27.46i. So then we need to convert that back into our polar form. So we would have our square root of the A value squared plus the B value squared. And then our angle will be our inverse tangent of our B value over our A value. So our radius will be 28.36, and our angle is going to be negative 1.32 radians. So the sum is 28.36 cis negative 1.32. Then we'll do our product and quotient up here. So for our product, we have 27 cis 30 times 3 cis 50. We'll multiply the radius, so 27 times 3, which is 81, and then it's cis 30 radians plus 50 radians is 80 radians. So that's our product. And then our quotient would be 27 cis 30 over 3 cis 50, which would give us 27 over 3, which is 9, cis 30 minus 50, which is negative 20 radians. This final problem here is in Euler form. So to add, we need to convert it to Cartesian. So we'll have r cosine theta plus r cosine theta for our a value, plus our b value, which is going to be r sine theta plus r sine theta times I. So that equals negative 0.699 plus 8.083 I. So we can find our radius, which is the square root of 0.699 squared plus 8.083 squared. And our theta, which is the inverse tangent of our b value over our a value. So our radius is 8.11 and our angle is negative 1.48 radians. So the sum is 8.11 e to the negative 1.48 I. For our product, we have 2e to the 50i times 9e to the 27i. We'll multiply our r values, so we get 18e, and then we'll add our theta values, so 50 plus 27 is 77i. So there's our product. And then for our quotient, 2e to the 50i divided by 9e to the 27i, we'll do 2 divided by 9, which is 2/9, times e to the 50 minus 27, which is 23i. So for these problems, it says write the following coordinates in polar, Euler, and Cartesian forms. So we have 6 plus 3i. So this is given to us in Cartesian form, and we need to convert it to polar and Euler. So we need to figure out theta and our radius. So theta is the inverse tangent of our imaginary over our real, and our radius is going to be the square root of our real squared plus our imaginary squared. So for our radius, we have square root of 36 plus 9, which is the square root of 45. For theta, our inverse tangent of 1/2 is approximately 0.464 radians. So to rewrite this in polar, we have our radius, square root 45, cis theta, which is 0.464. So that's our polar form. And then for our Euler form, we have square root 45 times e to the 0.464i. For the second one, it's given to us in polar form. So Euler form would be 27e to the 30i. And then we need to figure out a, which is equal to our radius, 27, times the cosine of theta, which is 30, and b, which is 27 sine 30. So a is approximately 4.165, and b is approximately negative 26.677. So our Cartesian form is 4.165 minus 26.677i. For this third one, it's given to us in Euler form. So our polar form would be 2 cis 50. And then our a value is 2 cosine 50. And our b value is 2 sine 50, which those are approximately 1.93 and negative 0.52. So our Cartesian form is 1.93 minus 0.52i. So one of the most important things to remember is to make sure that your calculator is in radian mode for these problems, because with our polar and Euler forms, the angle needs to be in radians. So here we have our first IB practice question. Before we read it, I want to note something here. x equals 4 cis 120 degrees. Because there's a degree symbol here, we'll need to use degrees instead of radians. But if there isn't a degree sign, we assume that the angle is in radians. So now we'll read the whole question. It says, using the complex numbers x equals 4 cis 120 degrees and y equals 3 plus 4i, calculate x over y and give your answer in modulus argument form and Cartesian form. So we're going to need to calculate x over y, which is dividing, and it's easier to divide in our modulus argument or polar form. So let's do it that way. So we'll switch our y equals 3 plus 4i to modulus argument form. So we'll draw our triangle. We have 3 as our real part, 4 as our imaginary part, theta and our radius. So our radius is going to equal the square root of 4 squared plus 3 squared, which is the square root of 16 plus 9, which is the square root of 25, which is 5. And then our angle is going to be the inverse tangent of 4 over 3, which is approximately 53.130 degrees. So in modulus argument form, our y equals 5 cis 53.130 degrees. So to calculate x over y, we'll have 4 cis 120 degrees over 5 cis 53.130 degrees. So we'll divide our radiuses. So that's 4/5 cis, and then we subtract our angles. So it'll be 120 minus 53.130, which is 66.87 degrees. So in modulus argument form, our x over y is 4/5 cis 66.87 degrees. So now we can convert that to polar form. We'll draw another triangle. 4/5 is our radius, and our angle is 66.87 degrees. So our a value will be 4/5 times the cosine of 66.87, and our b value will be 4/5 times the sine of 66.87. So those are approximately 0.314 and 0.736. So in Cartesian form, our answer would be 0.314 plus 0.736i. In summary, our polar form is where z equals r times the cosine of theta plus I sine theta, which is the same as r cis theta. And Euler form is z equals r times e to the I theta, where r is the modulus and theta is the argument. For our Euler and polar forms, when we want to add them, we convert to Cartesian and then add. If we want to find the product, we'll multiply our radius values and add our thetas. If we want to divide, we'll divide our radius and subtract our theta values. And then for Cartesian form, to find the sum, we'll add the a values and then we'll add the b values. To find the product, we'll multiply using the distributive property. And to find the quotient, we'll multiply both the numerator and the denominator by the conjugate of the denominator, and then we'll simplify. That's all for today's video. Thank you for watching.